Nope. So I can't see anybody. I hope you guys can see me. Monitors are off. Oh, there's Weston. Hey, there's Julia.
Your favorite student.
Yeah,
right?
What's going on?
Yep. Nothing. Thought I'd just stop by and say hello.
Awesome. Well,
See how you're doing.
How's softball treating you now?
Pretty good. Not as good as basketball, but
No.
You
Are
know.
you saying no triple championships? Is that what you're telling me?
I don't know. We'll see. We'll have to work really hard. I don't know.
That's good. So have you played any April Fool's pranks?
No, I don't know any good ones.
Oh.
Have you?
Well, I didn't play any, but I do know a good one.
Yeah.
This is one that my son did. He was working as an IT guy, and his supervisor was a little bit cranky all the time, and so he got his boss's permission, the supervisor's boss permission. And what he did on April Fool's is he took a screenshot of their desktop, right?
Mm-hmm.
And then he saved it as their wallpaper and then hid all of the icons. Then he took the screenshot and inverted it, so turned it upside down, and then physically turned the monitor upside down so that it looked right side up. So that every time she moved the mouse up, the arrow went down. And so she's freaking out. And then finally when she figured out how to get on one of the icons and she clicked it, nothing would happen because it wasn't a real icon, it was just a picture of an icon.
That's really funny, actually.
Oh my gosh.
Anyway, so he got her for like an hour. Everybody in the whole office was just laughing so hard. And anyway, that's the best one ever.
Yeah, that's funny. That'd get annoying.
Yeah.
That's so funny, though. All right.
Anyway, you ought to try something. I did have a friend, it's kind of late now, but she has a son that's in high school. And so what she did is she went into his room at about 6:30 and moved his clock ahead to read 8 o'clock. And then so she comes in freaking out, and then she says, "You're late for school, get up." And so he gets up, doesn't shower, just throws on clothes, hurries, drives to the school and gets there, and it's not even unlocked yet. The principal isn't even there yet. Because it's like 6:45. But then when he comes home, then she has breakfast waiting for him, so he wouldn't be upset. But anyway, I thought that was a pretty awesome prank. So.
That would be a good one. I'll try that one on my kids.
Yeah, that would be good. Well, did any of you guys do anything? Jada, Weston, Tobias, did you guys do anything? Or get pranked? No?
Someone in my school, they posted on their story to call someone's number and just make a Chewbacca noise, and then whoever did the best one would win or something like that. So someone's probably getting a bunch of phone calls.
Oh, that's awesome.
All they are Chewbacca noises.
Well, I did hear somebody at Mogion, I hope I'm not ruining the prank because I hope it wasn't on you, but in my trig class, they told me they were taking somebody's car of a student at Mogion High School and actually putting it on Craigslist for sale.
Oh.
So then they were going to get a bunch of calls about, this really nice car, and they're going to sell it for a couple $100, or I don't know how much, but anyway, I thought that was pretty good.
Can't be my car. My car is a piece of crap.
Yeah.
I'd buy it.
Yeah, that's all right. So, let's see. Oh, we're on 9.4. Okay, I was just gonna. So, anybody else do anything? Or pranked at all? Well, well, Julia, you ought to. I did I don't know if this is really a prank. It's not really, but I did post a thing on my Facebook that said, if your mom gives you grief about piles of clothes on your bedroom floor, just tell her it's a dead Jedi. Like from Darth Vader. But I don't know why I thought that was just hilarious, but anyway. So,
That's funny.
I don't have a dirty room, Mom. I just have dead Jedi in there. So anyway, that's kind of weird, but whatever. So
Good excuse.
yeah. Well, let us know how things go.
Okay.
So, but it's good seeing you, Julia.
You too. See ya.
Come by anytime.
All right. Bye.
We'll see you. Bye. Okay. So now we are, let's see. Okay, so I have that we were on this practice 3.5. So Weston, you're going to feel a little out of it until I get the videos. They were having problems with, I was hoping to get caught up on the posting the videos from last week, but they were having problems with it today. So anyway, so hope maybe tomorrow. Anyway, so we were talking about these. Anyway, 9.4. It's not that it's like super hard, but there's a lot of vocabulary, not a lot of new words. So anyway, so we were on this sketch several solution curves for this. Y prime equals y plus 1 times y minus 2. Okay, so the first thing that we do here, we want to find the second derivative. And so this is one where it might be easier to just multiply out and then take the derivative instead of doing the product rule. Now remember, we were running into this. Jade, I don't know if you remember on Thursday when we were doing these derivatives, you got to remember that when you do the derivative in terms of y, where like the derivative of y squared is going to be 2y dy dx. Or some people, instead of dy dx, will put y prime. And so it's the same thing. However, whichever notation you like. Okay? And so then you factor out the y prime or the dy dx, and we get 2y minus 1 times y prime. And then you substitute in what y prime was. So then y double prime is the y plus 1 times y minus 2 times 2y minus 1. Okay? So then you do the first and second sign charts. Okay? So the first derivative, let's kind of jump down here. So the first derivative sign chart is we had the zeros at -1 and 2. So here, let's just get rid of that. So at -1 and 2. And so that gave us 3 intervals. And so then you check into the first derivative, numbers on each side. So when we plug in a value to the left of -1, we got positive. Between -1 and 2, we got negative. And bigger than 2, we got positive. Then we have 3 values for our second derivative. We have -1, 2, and we also have 1/2, which basically splits this interval into 2. And so we plug in a value in each interval into the second derivative to get the sign chart there. Okay, now, to get these, what we did is we said, okay, so where the first derivative is positive, we know the graph is going up. And if the second derivative is negative, it's concave down. So then where the first derivative is negative, it's going down. Where the second derivative is positive, the graph is concave up. Where it's negative, the graph is concave down. And then in the last one, we get increasing concave up. So this is actually what we've done for the most part was from chapter 4 in Calc 1. Okay, so we're just kind of putting it with the differential equations. Okay, so now to draw the solution curves. Okay, so you graph the zeros, y equals -1. Okay, so this is kind of like a two-dimensional version of this one-dimensional graph here. So instead of points on the number line, -1, 1/2, and 2, you draw on the xy plane, y equals -1, y equals 1/2, and y equals 2. Okay, then you use the concavity here and say, okay, to the below -1, it was concave down but increasing. So you make this part of the graph here. And then from -1 to 1/2, it's going down, concave up. From 1/2 to 2, it was going down, concave down. And then from 2 up, it was increasing, concave up. So then, so where it changes concavity here in the middle, that is a point of inflection. And then to tell which solutions were stable, which equilibrium values were stable, in the two-dimensional, well, in the one-dimensional graph, it's the ones that where the lines come together, the arrows come together. In this graph, it's where these solutions come together. So where the arrows come together at y equals -1, that's a stable equilibrium. So you can either tell it from here or from here. All right, where the arrows go apart, that's an unstable equilibrium. So at y equals 2, it's unstable. So up here, the solutions are going away, so it's unstable. All right, so I know that was way too quick for Weston because he's just seeing it for the first time. All right, so hopefully when after you see the video and I do an example like that over a half hour, it's a little bit more palpable. But Tobias, Jada, did you guys do okay on that? Is that making sense, or do you need me to explain some more of it again?
I'm good.
Okay.
I understand.
So Weston, if before you'll have a week to do the quiz and get the video. If you actually need a little time, especially if the video's messing up and you need another day or two, just let me know to get it. And then in the meantime, if I'm in class, if you want me to go through another example or something, I'll be happy to do that. Okay. So anyway, I'm glad to see you back. It really, like I say, the math, I mean, you can actually see the math really isn't all that tough, but this section, there's a lot of vocabulary, a lot of kind of terminology there. So, all right. So the last little part of 9.4 is to kind of think about different situations, like where we've talked about Newton's law of cooling. So if you think of, like, taking a casserole out of the oven. So it's really hot, you put it on the counter. So Newton's law of cooling tells us how the temperature of the casserole is going to approach ambient temperature. Okay? Or if you take something out of the freezer and you're de-thawing it, well, its temperature is really low, but it goes up ambient temperature. So based on this graph, is this a stable or an unstable equilibrium?
Stable.
Stable, because it approaches from both sides. Okay? So it's a stable equilibrium. Okay? All right? Falling body encountering resistance. Regardless of the initial velocity, there's a value, like no matter, like if you are thrown, let's say if you parachute out of a plane, or if you don't have a parachute and you just jump out of a plane, okay? If you're Captain America, you could do that, all right? The gravity, the way that there's what's called terminal velocity, which means at some point you don't keep falling faster. There's like a maximum velocity that you will reach, okay? And it's based on your mass, gravity, and then where k is the rate of change. That involves a lot of other things, but it's mass times gravity divided by k. So kind of the rate of change that you're following. Okay, so it's a little different if you were, like a bullet has a different terminal velocity than something that's just dropped. Okay, because it has a different rate of change. All right, but whether something is speeding up or slowing down, there's this terminal velocity, which doesn't, it's not terminal in the sense that means you're going to die if you're going that velocity. It just means that that's the highest velocity that you can reach, okay? And in our atmospheric conditions and so on, okay? But just based on the graph, see, that's also a stable equilibrium. So terminal velocity is something that's also stable, okay? Another example, population growth. Says as a population approaches its carrying capacity, M, resources become less abundant and the growth rate decreases. This is logistic growth. So logistic growth means it has a logarithm in the equation. So I don't know if, I think we do logistic growth in Math 152, but you might not have seen it since then. Okay, so when you graph it, see, it goes from one horizontal asymptote to another. Okay, this logistic growth. And so the graph, if you draw like solution graphs, let's jump down here. Okay, they go from one horizontal asymptote to another, passing through an inflection point. And so these little S's, these solution curves, are called sigmoids. I don't know why it's messed up. Well, it's a sigmoid curve, okay? This little S looking thing. And so it is also a stable equilibrium, because like if you're talking about change in population, and M is the carrying capacity. So like think about like in a wildlife refuge, if M is like the perfect number of animals that can support in this wildlife refuge. So as the population approaches that number, well, if it exceeds that number based on resources, based on food, shelter, if it exceeds that, then they'll die off. Okay? And so then they die off, and then they go back to approach this carrying capacity, M. And so because the number, if it's less than M, then the population goes up. If it's greater than M, then the population goes down, that they're killed off. And so then population growth is also a stable equilibrium. Okay? The carrying capacity is a stable equilibrium.
Mr. Strong,
Yes, sir.
I think you should be on the Avengers and explain this to Thanos. That way, you're going to defeat
Yeah,
it.
you know, I know, right? He doesn't get that.
Yeah.
But then you could argue that Thanos is the ultimate predator. And so because the population has grown so much that it produced this predator named Thanos, that now he's making the ultimate correction in the population. So, I mean, he could argue that part too. So, but you're right. But anyway, that is kind of funny. That's a great application. But we're actually going to kind of continue on in that vein. So, but anyway, I just wanted to give some examples of a stable equilibrium in real life. Okay. So anyway, all right. I think, is that the last one? Yeah. All right. Okay, so that's it for 9.4. Now, and then, so today we're actually going to do 9.5. And it's a very short section. Is if you have the guided notes for it, you can see that it's just very short. Okay, so this, see, look, this actually only has 4 slides, the whole lesson. So systems of equations and phase planes. And so I'm only doing maybe a fourth of this section that I think that we need to worry about. Okay, so here we're actually going to do a competitive hunter model. Okay, so a competitive hunter, see, there's different kinds of models out there. So here maybe this is a model where the population of 2 hunters. So now we have, let's see, so now we have Ronan and Thanos, where they're both wanting to wipe out Xandar, right? And so anyway, but now all I'm thinking about is Avengers. Thanks, but that's okay. So so this competitive hunter model is basically, we're saying that, let's say that we have, I think we did, is it foxes and wolves and coyotes, okay? So dxdt is X is the number of wolves. So dxdt is the change of the wolf population, okay? And so in this particular example, we're going to say the change in the wolf population. Now notice that it has both y and x in the derivative, in the differential equation. Because what we're saying is that not only does the current population of the wolves affect the future population of wolves, but the population of coyotes affects the population of wolves. Okay, so it's a little more complicated. All right, so and then dy dt is the population of coyotes, and we're saying that it's affected by both the number of coyotes and number of wolves. All right, now the equilibrium point is when the population remains constant for a time. Okay, now it's kind of weird, but 0, 0, I mean, it kind of makes sense. 0, 0 is always the equilibrium point. An equilibrium point. It's not the, but one of the equilibrium points is when all of the coyotes and wolves have all died out, then the population is not going to change for a while until more of them are introduced back into the system. Okay? So, but usually 0, 0 is not what we're looking for. Okay? But that's one equilibrium point. So, what it's telling us here is that m divided by n and a divided by b is another equilibrium point for this competitive hunter model. So the way that we do it is we say, okay, so m and n are from this equation right here. So m is 4, n is 5. Notice that the negative is included in the formula. So n is 5. So 4/5 is the x value of the equilibrium point. A divided by b. So a would be 3, b would be 2, so 3/2. So what that means is based on the current population, when the population of wolves is 4/5 of what it is, and the population of coyotes is 3/2 of what it is, then we'll hit another equilibrium point, and the population of wolves and coyotes will not change for a while. Okay? And so the kind of this, to give you kind of a visual of what's going on, see if x, the x-axis represents the number of wolves, and the y-axis represents the number of coyotes. When these two values are reached, then the change in those is going to be constant. It's going to be, there's not going to be a change for a period of time, whatever you decide to make that. Okay, but this is so you're given this, and so then you basically just extract it from the problem up here. What's the value? So the equilibrium is 0, 0, and then 4/5 and 3/2 of the current populations of wolves and coyotes, respectively. Okay? Okay, so now let's look at another one. All right, so this one, so your practice problem is a predator-prey system. So the example was competitive predator. This is a predator-prey. So X is the number of rabbits, Y is the number of foxes living in a region in time T. All right, so the change in rabbits, the change in the rabbit population is A minus BY times X. The change in the foxes is negative C plus DX times Y. A, B, C, and D are positive constants. So remember that when I'm gonna have you take derivatives here in a minute. So A, B, C, and D are positive constants. It says show by differentiation that the function that this that this is constant when x of t and y of t are positive and satisfy the predator-prey relationship. Okay, so here's what I want you to do. I want you to see if you can take the derivative of this, of c of t, where a, b, c, and d are all constants. Okay? So just see if you can do that part. So take the derivative of this function right here. All right, who thinks they've got it? All right, Tobias, you looked up first, so tell me what you've got.
Yeah, I looked up and said definitely not me, but so just a quick question. So the derivative of a natural log is 1 over the natural log, right?
Yes.
So
Well, so the derivative of the natural log of y would be 1 over y, dy dt in this case, because it's a function of t.
okay.
Yeah?
I definitely did it wrong.
So
Then.
see, if you just had thought of this as the natural log of x, the derivative of natural log of x is 1 over x. Okay? But when you're taking the derivative of y with respect to a different variable, then you have to throw in the dy dx, or dy, in this case dy dt, because it's a function of t. Okay? So now what do you do with the a?
I want to say, would you just leave it in front?
Yes, you just leave it in front. Okay? So this first derivative then, so a times, so 1 over y dy dt, or however you want to write that. All right, so then what about the derivative of negative by? What would that derivative be?
Is this still me?
Yeah,
Would it be b dy dt?
so it'd be negative b dy dt. Okay. All right, so Jada, what would the derivative of negative dx be?
Would it be dx dy dt?
Okay, so the derivative of, what's the derivative of like negative 5x?
-5.
Negative 5. So you drop the x, but you will have the dx dt. So it'll be negative d dx dt. All right, and then, so Weston, what would be the derivative of c ln of x of t?
C times dx dt over x.
Yes. Okay. All right. Any questions? Okay, so now what I want you to do is see this dy dt and this dy dt, replace it with this dy dt, what dy dt is equal to. And then what dx dt is equal to here, replace that with the dx dt here and here. And so then you're going to have a big, long, messy thing, and then I want you to use some algebra and simplify. So substitute in the dx dt and dy dt. Whoops. I didn't want to reveal that next slide, or that next line. So substitute in the dx dt and the dy dt, and then simplify. Okay, so what I'm wanting here is, well, let's just, so in place of dy dt, you're plugging in negative c plus dx here and here. And in place of dx dt, you're plugging in a minus by here and here to get that. Okay. So everybody good so far? All right. So now here the y's cancel in this first term. And so I can distribute the a. Here I can distribute the negative b and the y. Here I distribute negative d and the x. And here the x's cancel and distribute the c. So go ahead and do that next step. All right, so Weston, what do I get?
Just after the y's and the x's cancel,
Sure.
you get a times negative c plus dx minus b times negative c plus dx minus d times a minus by times x plus c times a minus by.
Okay. And so
Oh yeah, and then
so then I just went ahead and I went ahead and distributed there. Okay. And so now what am I doing here? I'm looking and there's all these like terms here. I guess I should make it a little easier. But it turns out everything cancels. Okay? So negative AC plus AC. And then you have ADX minus ADX. Then you have BCY minus BCY. Then you have minus BDXY plus BDXY. And so when you combine all the like terms, you get C prime of t equals 0. Now, why is that important that you get 0?
Is it because it's the equilibrium?
Yes, that's it. That's it. Because, see, the equilibrium point means it's not changing for a while. So that means its derivative is 0. That's exactly it. Okay? So that's what hopefully we were going to get, was that the derivative is going to be equal to 0. So it's saying if it satisfies the conditions, okay, it satisfies this function and the predator-prey system, which is this right here, then we get an equilibrium point. Okay? All right, well, that's it for 9.5. Little symbolic manipulation there, systems of equations. Okay? Now, and that's it for chapter 9. So, one thing that's going to be a little different in chapter 9 is that while I don't think You know, it's interesting because my morning calculus class thinks that chapter 9 is super easy. Okay. But what I have found is that on the test, when it's, you know, when all this stuff is mixed in, you kind of forget it's the vocabulary that you struggle with. So what I'm going to do on the chapter 9, just because everything, the vocabulary is different, is that I'm actually still going to give you 2 shots at the test, but I'm going to take your highest score, not your average score. So, but give it your best shot the first time, but just know that you'll be able to correct your mistakes and take it a second time and just take your highest score. This is the only test I do that on. Okay. And again, it's not because it's so hard. It's just that the way things are worded sometimes I think is a little bit tricky. Okay. So, but I will post the 9.4 and 9.5 quizzes today, and then I'll probably post the chapter 9 test tomorrow so that you'll have a week from tomorrow to take it. Okay. All right. So any questions on that? And then, like I said, Weston, is if during this week, we're going to start on chapter 10 tomorrow. And but if any of you have questions from what you're doing in chapter 9, don't hesitate to come and we can work on those. Okay. Because like I say, really, so my morning class, when I'm with them, they've asked me a lot of questions from, the practice problems. I'll get at least 1 or 2 a day. But then once I show them, and they're like, oh, that's what we're, it's like, oh, yeah, that's it. So they feel like that once they understand what the problem is being asked, and so hopefully if you have your guided notes in front of you and so on, then you'll be just fine. But that's the only thing I worry about, really. So make sure you do some practice problems, to look over the quizzes, that kind of stuff. All right? So any other questions, comments, concerns before we call it for today? Because I'm not going to start chapter 10 with only 6 minutes to go. Okay, well, that's it for today. Thanks, you guys, for working hard. Glad to have you back, Weston. Hope you guys have a good week, and we'll see you tomorrow.
I won't be here tomorrow. I have a baseball game.
Baseball game? Everybody else going to be here tomorrow? Okay, so I think I've already put out the guided notes for 10.1, but just make sure you get it. Chapter 10 is, I think, one of the easiest chapters in all of calculus. But you got to just, get the hang of what we're doing. Okay? So you'll be okay. But tomorrow will be a good day for you to be gone. You'll be just fine. Okay? All right. We'll see you.